Welcome all to my lecture series on MOS and MOSFET. Myself, Orpon Deashi, from the Department of Electronics and Communication Engineering in RCC Institute of Information Technology, India, welcome you all to this lecture series. This is the fifth lecture of the six lecture based series on MOS and MOSFET. The previous four lectures are already available in my YouTube channel. So if you want to brush your knowledge related with some small mathematical terminologies or some conceptual matters, then you can revisit to my channel. You can get the YouTube video and just brush up that part. So far, at the beginning of my lecture series, I have mentioned that I will try to cover up this portion of MOS and MOSFET with 6 lectures. The 3 lectures will be dedicated for MOS capacitor and rest of the 3 will be for MOSFET. As usual, if I recapitulate, the first lecture is on the band diagram of MOS capacitor, discussed in detail for unbiased condition as well as for various biasing conditions. And though I have drawn the band diagrams for p-type substrate, but also I have discussed the variations for n-type substrate also. And with that, I have moved towards the electrical characteristics of MOS capacitor, which are discussed in lecture 2 and lecture 3. In lecture 2, I have discussed about the charge potential profile of MOS capacitor. In lecture 3, I have discussed about the capacitance voltage profile of that. And I have discussed for all accumulation, depletion, inversion, even the flat band point also. If you just look at those lectures, you will find that all the detailed mathematical steps are clearly shown. And then I have proceeded towards the MOSFET. And at the beginning, I have mentioned that MOS and MOSFET are not same. Not though maybe looks same, but no. The terms people confusely used for others. Looks means the alphabets. The first 3 alphabets are same, but that's not the same. MOSFET is a 4-terminal device which is a transistor, and MOS is a 2-terminal device which is a capacitor. And in lecture 4, I have shown why MOSFET is also called a 3-terminal device, not a 4-terminal one, because the body effect. And what is the role of the body effect? I have shown with some formation of, say, virtual diodes. And I have shown why source and body are shorted for both p-type as well as n-type substrates. Also, I have discussed the not in very detail, but at least I have qualitatively mentioned the enhancement mode and depletion mode MOSFETs so far. So these points are already covered. I have said that the formation of inversion condition is extremely useful. It's required. And the structural composition of the MOSFET, that is n-channel MOSFET, I am showing here with p-type body, n-channel, gate and insulator. If body and channel is not also mentioned, but if you find that drain is positive, source is negative, as well as gate is positive, naturally it will be n-channel MOSFET. Very simple. For p-channel, the source will be positive and drain will be negative and gate will also become negative. And source and body will be sorted also. That's a simple thing. So you know all these sort of things. I am not going into express it and going for more details again and again. This just recapitulation of our lecture 3. So I am not going for this again animations and the discussion so far. And this is the inversion band diagram. I have just put it because just to clarify what inversion is, that the intrinsic Fermi level will bend and goes below the extrinsic Fermi level, and extrinsic Fermi level will be very close to the conduction band now, which means the p-type substrate becomes n-type, at least some part. And why? Just because of the accumulation of the minority carriers, a heavy amount of accumulation. So depletion turns to inversion, and you will get the point of inversion, which is very clearly shown by the blue color circle, which is shown in the background. If you look at the junction, you will find it. And what is psi f? Psi f is the Fermi potential. What is that? The distance between the intrinsic and extrinsic Fermi level. But where it will be measured? Not the part where intrinsic Fermi level starts to bend. It's the part where both are parallel. And psi s is the surface potential. What is that also? That's the total amount of bending of the intrinsic Fermi level. And where it will be measured? It is measured at the surface of semiconductor. That means it should be at the insulator semiconductor interface, and that's very much required for this measurement. And I have shown the formation of N channel by a green color shaded portion, which means that portion minority accumulation is heavy. So if you move from left to right, conducting region, insulating region, N channel, and then P substrate. So it's a 4-layer. Beautiful concept. That's a 4-layer device. And the potentials are also discussed. So in this part of this part 1 of the electrical characteristics, I will discuss major 3 portions. First one is the calculation of the minority carrier concentration, both at depletion condition as well as inversion condition. Similarly, if I move for the second case, that is the I can say the threshold voltage calculation for a MOSFET, the ideal threshold voltage. And the next part, which will be a consequent or extension of the second part, that is the change or shift of the threshold voltage in presence of body effect. The body effect I have already discussed in lecture 4, the last 2 slides. So I want to go for that repetition. Repetition merely just kills time. So I want to make the lectures compact as much as possible. So for these 3 mathematical derivations will be discussed. So without wasting time, I am going for the lecture 1, the first part of the derivation, and that's nothing but the minority carrier concentration. And naturally, once if I write the term minority carrier, it will be either depletion or inversion condition. Accumulation is never possible, because you know that accumulation condition means it's the upward band bending and there will be majority carrier accumulation. So I am going for minority accumulation, it's not the majority accumulation. And you know from my lecture 2 that any sort of electrical characteristics, if you want to analyze, study, it begins with the Poisson's equation. And since the variation of the potential or say variation of the charge is in along the z-axis, as per our figure, you may write x, y, whatever. Doesn't matter, any of them Cartesian coordinates. So it's according to this figure, it's along z-axis. So naturally, we will consider one-dimensional Poisson's equation. And that greatly relieves us, because solution of 2-dimensional Poisson's equation is extremely difficult. You have to go for numerical techniques, unless it is decoupled. So for one equation, you know the equation that d2 phi dz2 side dz2 equals to minus rho by epsilon, or d dz equals to rho by epsilon, whatever, in terms of potential or in terms of electric field, whatever you can choose. Now what is rho? Rho will be the charge carrier density, and you know it. It will be minus q into Na. Why negative? Because you are considering the substrate is majority and you are calculating minority, so there will be a sign reversal. And if you look out the QV characteristics derivation in my lecture 2, as far I can remember, the same convention we have adopted, that ND should be positive and NA should be negative. So I have adopted the same, and rho equals to minus Q NA. And your expression Ez from Poisson's equation is integration of rho by epsilon dz. Though it's an indefinite integral, but I will substitute the boundary condition so far, and naturally it will become a definite integral. Obviously, definitely you have to solve a definite integral, otherwise you can't reach to a meaningful conclusion at the end of your mathematical derivation. So far I am considering it is a definite integral, and later, because once I am substituting the value of rho, it will be minus QNA, so Ez will be minus QNA by epsilon dz. And so far, if I integrate, there will be an integration constant, it will be C1. So what you will get, you are getting that Ez equals to some value of z plus some constant. Now, as per our rule of integration, you have to calculate the constant. So if you go for z equals to 0, what is z equals to 0? At the insulator semiconductor surface, and the value of electric field equals to E0. Similarly, if you go for z equals to W, what is W? Depletion width, then field equals to 0. Now the second point has a physical significance. The term W is very simple. One can say it's a depletion region width, but what is that? Depletion is nothing but the minority carrier concentration. So it should be either depletion or inversion. So Z equals to W means where the variation of the minority carrier ends. That means after that it will be all majority carriers. And if all the majority carriers, then there will be no change of potential, no fluctuation of that. So if there is no fluctuation of potential, d phi equals to 0, E equals to minus of grad phi. So naturally the gradient of phi equals to 0 means field equals to 0, and I have put that boundary condition. And why I am explaining, because if you substitute the second boundary condition, you can very easily get the value of C1, which is QNA by epsilon into W. So the electric field expression is very simple to all. It will be QNA by epsilon W minus Z. So you will get the variation of field. Simple for both depletion and inversion, no problem. And if I substitute that E equals to minus grad phi and one dimension, so it will be d phi dz. And if you integrate, naturally d phi equals to minus QNA by epsilon W minus Z dz. Again, you have to put the boundary condition, and these boundary conditions are already given in the third slide of this lecture. That is the band diagram. And what is that? At Z equals to 0, again at the surface, you know it's nothing but the surface potential. So I have written exactly same. And at Z equals to W, where your minority carrier concentration ends, naturally it will be Fermi, because now at that point, the intrinsic and extrinsic Fermi level starts to become parallel. So it will be simple, it's the bulk, the beginning of the bulk, and it will be the Fermi potential. So I have put those boundary conditions. So Fermi minus surface is this value. Now there is a trick. I am calculating for depletion. So for depletion, naturally Fermi is greater than surface. So W looks my negative. So that means I have to take the mod. Otherwise, you can't make a length negative. So W equals to 2 epsilon by QNA psi f minus psi f to the power half. A simple calculation, but once you go for the numerical analysis or say some data-based calculations of some mathematical problem, please be cautious, you have to take the mod, otherwise you can't get the actual answer. Now under depletion condition, the Fermi is less than the surface. But under inversion condition, surface is greater than the Fermi. And if you go for the magnetic carrier concentration, now the actual part, what is the value of a charge? You know that width multiplied by charge density. That's the basic formula. W multiplied by rho, and rho is minus QNA. So if I substitute it, then QD equals to minus QNA, and that part I have discussed earlier. So a simple calculation, QD becomes minus root over 2 epsilon QNA mod of psi s minus psi f, surface minus Fermi to the power half. And once you will get QD, then I will put the onset of inversion. Onset of inversion, you will little be amused that psi s would be equals to psi f, but not. Measurement is in different direction. Psi f you are measuring from naturally some extrinsic Fermi towards the intrinsic Fermi, and the bending is from the intrinsic Fermi or total, so it's measured from the higher level to lower, so direction is reversed. So surface and Fermi are negative, and naturally every calculation should be based on Fermi, not based on surface, because surface, that will be variable quantity. You can't consider surface potential as a reference, because at different depletion bias it will be different, at different inversion bias it will be different. You can't set it. So naturally for inversion condition, I have to calculate again Qi, and which will be some function into obviously the minus of 2 psi f of mod. So total depletion or inversion charge may be negative because this is minority. So simply the negative sign indicates it's a minority carrier, and I am getting the magnitude of the charge for both depletion and inversion conditions. The next part of this lecture is the threshold voltage calculation, and I am going for that. For ideal threshold voltage, you know it will be sum of the flat band plus the threshold of a MOS capacitor. Why? Because threshold voltage of a transistor means what you have to overcome a voltage after which you start to get current. So that means you have to start your journey from flat band, because below flat band it will be accumulation, no much required, and after that you have to set a capacitive action. So at least you have to make the capacitor, so it will be V ideal MOS capacitor. So what will be the VTO? I am coming to that. So it will be 2 psi f by QB by COD, and I will come to that. So VI MOS it will be, sorry, there is a mistake, it will be VI MOS. VI MOS equals to minus of 2 psi f plus QB by CD. Because VI MOS for MOS, it will be twice of psi f, it's very simple because it will be twice of Fermi level, plus some additional potentials it will come because it will be bulk by dielectric constant, there will be bulk charges stored, so naturally it will be that terminology come. Similarly, flat band, it will be the work function difference between metal semiconductor at the flat band condition subtracted by the fixed charges, because you have to go for, there will be some fixed charges always comes because of the surface states. So the imperfections I have considered, if you consider it's a perfect material, then you will put QFC equals to 0 and VFB equals to minus of phi ms. But if you put that value, it will be minus of QFC by CD. And so phi ms, again the metal semiconductor work function difference of half of the band gap minus of Fermi potential. So all together, if you put, then VTO equals to minus 3 psi f minus EG by 2 minus Q by CD minus QFC by CD. The derivation is for 5 lines. That's not my target. My target is what are the functions the threshold depends. Look, it depends on the dielectric capacitance. So that's simple, oxide capacitance or whatever the dielectric you are using. It depends on the bulk charge. Obviously, for capacitive you require the bulk charge. It depends on the fixed charge if you consider the surface states, and if you go for later on your works, the surface potential is an extremely important factor in the surface states, which basically comes into the nanometric materials, and it's a very important for nano device design. Band gap, so material parameter is extremely important again. And Fermi potential, the difference between the intrinsic and extrinsic Fermi level. So altogether, these are the critical factors that gives you the VTO. So if I go for the body effect, I have already discussed, which is nothing but this term so far. So body effect is a simple term of what are the diode formations I am showing, and naturally if source and body are not connected, then you will get a diode formation, and that's why I have bring the same slide we have discussed in lecture 4. So I'm ticking it. And now this is the QI, the first expression. We have considered that it's a MOSFET is a 3-terminal device. It's perfect. But if the body effect comes, then obviously the Fermi potential will be modified, and Fermi potential will be added with a function called surface to body potentials. Now, source to body potential, it starts to develop. And what it tries to do, it tries to make a hindrance of the carrier flow. So naturally, the inversion charge in presence of the effect, so it will be added with the say Fermi potential, and once you have added, you will get the term. Then what will be the change of the space charge density or the charge? It will be delta function, so you have to subtract them, and if you subtract, this will be the expression. Obviously it will be later I will discuss the body effect coefficient related with this, but not in this lecture. I am going for that, but what I am showing that it depends on these factors, and the change of threshold voltage, that will be the delta QSB by CD. Naturally the change of charge divided by across the capacitance, so you have to divide the expression of CD, and that will be the expression of delta VT, that is the shift of the threshold voltage. So altogether we are getting this shift of the threshold voltage from these expressions, and that's the derivation. And you can consider this 1 by CD root over 2 epsilon QNA. This total term is called body effect coefficient. Later I will discuss it in my lecture 5 in more details. Once I am going for VT for IV characteristics, I will discuss in more, but let me just briefly remind it. The 1 by CD root over 2 epsilon QNA, it is called body effect coefficient, and it will be known as gamma. And gamma has a unique unit. Its unit is root over volt. If you surprise, I am giving a small clue that VT is the unit of volt, and root over something 2 psi f or 2 psi f plus VSB, it has a unit of root over volt. So if you make a dimension analysis, the body effect coefficient, the unit comes of root over volt. That's a very tricky, but you have to remember the body effect coefficient. Actually this term gamma, that is 1 by CD multiplied by 2 epsilon QNA, we will call it in some later derivations, and these are extremely important once we go for the analysis of the MOSFET device, the IV characteristics and everything. I will go for step by step, and I will call it the body effect coefficient, and what are the functions, how it can affect the what is the role of the VT or the change of delta VT. Actually, when I'm going for the short channel effect discussion, then the body effect coefficient will be extremely crucial for this analysis part. So thank you all. These are the small mathematical steps in order to understand the electrical properties of the MOSFET. And in my lecture 6, I will discuss in details that IV characteristics of the MOSFET, both in the active and saturation condition. And I will also discuss the channel length modulation. Thank you all.